This video is sponsored by PCB. Welcome everyone. In this video I'm going to continue the work with the previous topic, which was making a scale out of a PCB. And in the previous video I made this device here, which was basically a PCB-based scale. And the original idea here was to create a pattern on the PCB board and use it as a strain gauge, and then have a circuit, which is a Wheatstone bridge and an operational amplifier to, let's say, process the output signal, which is just a voltage change from the Wheatstone bridge, and then use basically the structure of the PCB, which is here a cantilever beam, to detect weight changes on this end. But the original idea was not working, so I just placed the strain gauge on the PCB, and then that worked, of course. But this was a small, let's say, proof of concept test. And now I designed a more advanced PCB, which you can see here. And this is actually a self-contained balance or weighing scale. And we will see if it works or not. But as you can see, this is a relatively small PCB, not too big. And it actually contains everything. So if I assemble it and if everything works, then this small PCB can be used as a scale. So what this has is, you can see that here and here we have like four areas, both on the back side and the front side as well. And I drew those areas to mark the places of the strain gauges. So what we will have here is that at these 4 points at the outer parts, this PCB will be supported by some pins. So they will be basically the legs for the PCB, just to put it down. And then on these 4 points I will have another set of pins which will support a small tray on top of this whole thing. You will see when I assemble it. And then when I will put a weight on that tray, that will push down these 4, let's say, holes. And then it will bend the PCB to some extent. And that bend or bending will be registered by these 4 strain gauges. And then that will be processed by the rest of the circuit. And the rest of the circuit is actually very simple, because I use an HX711 chip, which is specifically made for these Wheatstone bridges. And then the output signal of it is handled by an AT-Tiny85 circuit. And then the weight or the signal proportional to the change within the Wheatstone bridge will be displayed on a small OLED display. And everything will be self-contained. So on this side of the circuit, I put a circuit which is just a battery charger. So this circuit will be operated either by a USB external voltage source, or a battery which will be somewhere glued on the back of this board. It will be a small, I think 380 milliampere hours battery, a lithium polymer battery. And since I will be using 4 strain gauges, then the Wheatstone bridge will be a full bridge. So all 4 strain gauges will participate in the measurement. And then that will be the working principle of this circuit, basically. And I will have to be careful how I install those, but I will show you in a drawing, and I will explain it more clearly how and why we install the strain gauges in a certain pattern. And then since some of the components are SMD components, I made a small stencil, as you can see. So this will help me to apply solder paste where I need it. So there is a few parts on the right side, and there is a few parts on the left side, and then I have basically just 3 through the whole components: the AT tiny microcontroller, the connector for the lithium battery, and the connector for the display. And yeah, of course we can mention the 4 strain gauges, but that's more or less obvious that they have through the whole connectors. So that's all regarding the plan. So as I mentioned in the beginning of this video, the video is sponsored by PCB. They provided me these gorgeous PCBs and also the stencil, so I could make this project for you and show it how it works. And if you want to have similar PCBs or this specific PCB or 3D printing or machining, visit their website, link is in the description, and you can find the suitable service for you. And also don't forget to visit their website and check out their 5th PCB design contest, where you can register your project until the last day of this December, and then you can participate in 3 different categories, and you can also win very valuable prizes. So don't forget to check out PCB-based.com. So without further ado, let me prepare the parts, and then we will assemble this board, and I will explain how I assemble the things and how I attached the certain parts. Alright, so everything seems to be in place for the assembly, so I just quickly go through the parts, and then I will show you a close-up video of me applying the solder paste and then assembling the things and soldering the board. But as I said, this thing will be operated by a lithium polymer battery, so that's here. And then we have an OLED display, the 4 strain gauges, and as usual I kind of cheated a little bit, so I have already laid out the components, the SMD components, on an empty board. And then what I will do when I record the stuff, the close-up pick and place part of the video, I take another board, I will apply the solder paste on this one, and then I just pick up here from the corresponding spot and then place it to the same spot on the board which has the solder paste. And then I do this one by one, and it makes my work easier because then I don't have to unpack everything one by one. There was like 12 bags or so to get these components out of their bags, so then everything is prepared. Then a USB connector, a socket for the AT tiny microcontroller, and another connector for the battery. And then here I have these guys, they will be the legs for the unit, basically, for the PCB. So this long guy will be in this part. This is the, let's call it, static part. This will support the whole board. And then this will come in here like this. So on one side it will be supported by a nut, and then on the other side I will have this transparent stuff. It will come on the top. It will be functioning as a tray. So I will have the 4 screws here, and they will be mating with this, or these 4 standoffs. So that's that. And then I have the solder paste prepared, and obviously the stencil. So then stencil goes on perfectly like this. And then I will just scrape off the excess solder paste with this scraper or spatula. So let me prepare the camera, and then I will show you a nice video, hopefully. So as I can see, there is no short circuit, so the soldering was more or less successful. And now I have to solder the components which have to be hand soldered. For example, here we have the socket for the microcontroller, and then there will be a plug or connector for the battery. Then there will be another connection or socket for the OLED, as you can see. And of course I have to install the 4 strain gauges, 2 at the bottom and 2 at the top. And I think I would start with the strain gauges because they are relatively flat, and all the other components which I'm going to install are kind of protruding from the surface, and that would make the installation a bit more difficult. So let me prepare the strain gauges and then I will show you how I install them. So let's install the strain gauges, and how we have to do it is the following. We are using a full bridge configuration, which means that within the Wheatstone bridge all the 4 resistors are now strain gauges, but we have to install it on basically a cantilever beam. This can be imagined as one part of the beam, and the 4 different strain gauges have to be installed in different ways, and it will look like the following. So 2 strain gauges inside this Wheatstone bridge will be on the top side of the PCB. I will install them first, and those guys will be the resistor number 1 and resistor number 3, or strain gauge number 1 and 3, and they are the opposite sides of the Wheatstone bridge, diagonally, let's say. And then on the bottom side we will have the strain gauge number 2 and strain gauge number 4, and those are also diagonally on the opposite side of the Wheatstone bridge, but they will be at the bottom. And therefore, when we put a weight on this hole right here, so we push it down, all these ears, this guy here, this guy here, and this guy here will be pressed down in the same way, of course. They will experience the load divided by 4 on each, let's say, holes or pads. I mean, hypothetically, they are not perfectly in a square probably, but what I want to say here is that if we would put all the strain gauges here on the top at each 4 locations, so 2, 3 and 4, then each strain gauge would experience only tension, because this goes down and then there will be a tension here, but that is not good from the strain gauges arrangement. So what I will do, this is the number 1, and this becomes something which experiences strain as tension. But then on the other side I will put it on the back side, because this is the number 4, and it should be at the bottom, because it should be in compression when this is pressed down. And how we reach that is that when we compress a cantilever beam, we know that the top is always in tension if the force is applied here downwards, and then the bottom side will experience compression, and that strain gauge, which should end up here, should experience compression. So we will put the strain gauge on the bottom, and then here number 3, that should be on the top, so that will be fine. And then again here number 4, that goes, or number 2, sorry, this goes on the bottom. So this will be 2, this will be 3, this is 4, and this is 1. So let's start with 1, and I explain how I do it. So you can see the tiny strain gauge here, and I will just pick it up using simple tape. Like this, and I put this aside now. And then we return to this ear. I clean it. Then I drop a few drops of super glue on it. And then here comes the strain gauge, and I try to apply it in the center of this grid or square. Now it's there, so this has to cure for a while. So meanwhile, I know that I have another top position, which should be the strain gauge number 3, which is the diagonally opposite corner. So this guy here. So then I do the same exercise here. So while the glue is curing at the corresponding places for the strain gauges, then I can install the components here and also here. So I can hand solder those while the glue is getting dry. So here is one thing that we have to be careful about, because I haven't mentioned this thing, but it's a thing. So you can see that these wires are actually covered by an enamel layer, which is an insulating layer. And that you have to remove somehow, either before gluing the strain gauge, probably that's the best option, or after. And I show you what's the difference between having removed the enamel and not having removed the enamel. So you see one probe here at the left side, and then there is a connection here. But then here there is no connection. It's soldered, but actually maybe it's even visible that there is no metallic contact between the solder material and this wire because the enamel doesn't let the hot solder, the molten solder, to wet the surface, because it's not a metallic surface which it can stick to. And the enamel doesn't stick to the molten solder, or the other way around. Therefore, there is no metallic contact on the two sides of the wire. So how we should tackle this thing is that we should remove the enamel. And I will show you one thing, is that it's quite easy just to have this wire. I try to show it in a better perspective. And then simply take a knife. You can see that this is quite small, and start scraping just at the solder. So I just remove this a little bit and try to scrape it. And then let's measure this thing. So one probe comes here, and there is still no connection, as you cannot hear it. So let's continue the scraping work. Let's measure again. So it works, you can hear it. But this doesn't mean that it is connected to the PCB, it just means that this surface is now exposed. So then we have to put a small blob of solder there. And now we have the contact. And actually I can measure it between R3, because that's where it goes, as you can see, just to prove that it works. So R3 is here, and it works. I'm touching the tab on the strain gauge now. So it's connected. So everything is assembled now, as you can see it here. So we have the strain gauges. One is at the top here, another is of course at the bottom, as you can see. And then here is another at the top, at the bottom. So tensile, compressive forces are, let's say, registered. And that's how the full bridge has to be assembled in this kind of configuration. And then we have the HX711 chip here, and then the 80 tiny chip, and then we have the OLED display, and then a USB connector, and under this part we have the battery management and the charging circuit. So basically that's all. And how this circuit will be completed is that I have this tray prepared, nice plastic tray, and then that should go on top of this circuit, as you can see, something like this. I will fix it off camera. And another thing is that I will use a double-sided adhesive tape, and then I will just glue this guy somewhere at the bottom, and that will be the power source for this. It doesn't have any on-off switches, so that might be a bit inconvenient, but what I would do is that I would just break this cable somewhere. Maybe I will do it in this video, and then I will just put a small switch, because it's easier to switch on and off than just adding anything to this circuit anymore. It's a final version. So let me do those things off camera, and then we test how this thing works. So the plastic sheet is installed, as you can see, and then on the back side there is a battery with a switch. So of course now the circuit is broken because the switch is in the off position. So I just flip the switch. Then we immediately see that something is going on. So we have the status LED there, and we have some message on the display. I added some delay, namely 15 seconds after I turn on the switch. There's nothing happening to the circuit. It just hangs. And now tearing is going on, which does 100 readings, and then it prints the outcome here. And the tearing should bring the weight to 0. But now, as you can see, that the weight is actually drifting. So I have to figure out why it is drifting, but at least I can say that the communication is working with the HX711 module and the microcontroller. So at least that's fine. But for some reason there is a drift. And if I put some weight on this, then that should be at least registered by this. So now the recent reading is like 13,100 and something. So I just put a battery there, and now it immediately jumped to minus 21,000. So that means that whenever I have a load on this, then the number will decrease. So it will get more negative. And then I guess when I would remove the load, so I try to push this upwards, then the number should be more positive. And that's correct. So that also means that probably my Wheatstone bridge is upside down, because the additional load should actually cause more positive numbers. And if I decrease the load, which means that now I'm lifting the table, that should cause more negative numbers, because it's pulling. But it doesn't matter, it's just an absolute value operation, and then it's done. Nevertheless, I have to figure out why this thing is drifting. So let me work on this a little bit, and then we will figure out what's wrong. So here is the fixed thing, and as you could see it in the clip, the problem was, or the problem which I suspect to be the problem was that there was an air bubble under the strain gauge. I could not really decide if that was under it or something, but nevertheless I removed the strain gauge, I scraped it off with a knife, and then I reapplied another new strain gauge, and I was hoping for the best. But it can be that, for example, the glue which I'm using is pretty much old, so it does not provide sufficient adhesion. But let's turn this thing on. And let's wait until it gets taired. That is done after doing 100 readings. And then that reading is, or the average of that reading is subtracted from all the subsequent values. And now this is an empty scale, but you can see that the value is drifting towards the more negative values, minus 2500 now, and it will get worse and worse. And one thing for the drifting, I still suspect that the adhesion for the strain gauges is not perfect, so there could be one reason. And another reason, which I also just suspect, so I'm just speculating, is that the holes here are not perfectly drilled. So it can be that there is a small tension caused by the tightening of these 4 screws. So when I tightened these, then there is some kind of tiny deformation in this plate, and that deformation also puts some stress on these cantilever parts on the 2 edges of the board. And as the stress is relaxing, then the drifting happens, basically. That's what I suspect, but that is just some speculation. But now we can see that the drifting is not that strong, so it's getting more and more settled down. So it could be that there is something electronically with the circuit. One thing could be that something is reaching its operating temperature, probably, or something like that. I don't know. But let's put a weight on this and see what happens. So there is a 100 gram here, and I just put this on the scale. And now it goes to minus 20,150. And then you can see that it goes a bit more. So now it's minus 20,180, but it was 20,000 and few hundred as well. So you can see that it changes, but now it's more or less stable. And then of course I can replace this weight with another one. So I remove this, and let's put just 10 grams on this top. And that is barely noticed by this circuit, but it's there. So minus 4,400, 4,700, 4,900. So it's drifting, as we can see, unfortunately, but it kind of works. And one more feature which I haven't shown is that it has status LEDs for the charging. So now the charging is a bit tricky because I have a stripped USB cable, so I have to connect that first to the power supply, and then I connect it here. I'm trying not to bounce anything too much. And now I turn on the power supply, and you can see the red light, and the red light is showing that the battery is being charged. And then that light will flip to green. There is another LED next to it. And then that green light will show up when the battery is full. So let's see it once again. Put this on. And again it's minus 19,500 something. So it kind of works, but probably could be better. But I think the concept works nicely. So this could be used as a scale now for measuring smaller weights or even larger weights, because there is a lot of flex available in the, or flexing available in this amount of material. So basically this is what I wanted to show you. So now I made my own tiny scale. It has to be calibrated, but that's not a big deal. If you visit my website, link is in the description, then you will see how to calibrate such things step by step. And then that is also valid for anything which has a linear relationship between the output value and the measured value. For example, voltage versus temperature or things like that. That principle which I show on my website can be applied on this. And also, if you want, you can support me on Patreon. And don't forget to visit PCB-based website, because you can buy this specific PCB if you want to build this circuit for yourself, or you can use their services to build your own custom circuit. So I hope you learned something. I hope this video was useful to you, and see you in the next video.